When you said free lunch, maybe you mean lunchtime is free rather than we get free food.
Yeah, so you're free to go where you want. Go to Pipiolo if you want. Okay.
Thanks, Daniel, for the introduction. So welcome everybody to the conference. So let's start doing some math. So our first speaker today is Pierre Colmes from CNRS and Sorbonne Université. He's going to speak about completed cohomology and group cohomology.
So
maybe I will give you
I don't know which one of them, but this one's good.
this one is good.
Yeah.
And this one was here, so probably is good too.
Excusez-moi, il y a un petit souci avec
Ah, ça, je peux avoir ça pour.
Ouais. Parce que je pense que les crayons sont plus forts. Ah ouais.
Okay, so first I want to thank the organizer for inviting me in Chile. It's my first time here, and so far I enjoy it quite a lot. So I will not repeat the title. So I start with some notations. So L is going to be a finite extension of QP, which will serve as a field of coefficients for all the representation we are going to consider. A is the adels of Q. And then I have strange notation. So these are A infinity means that I take finite adels, so adels outside of the real numbers. If I want to remove P also, maybe I should say that P is a prime number, but etc. And if I have an adel, and if I have a finite number of places, I can write it in the following way. So that's the contribution of the places in S, and that's the contribution of the places not in S. Okay. Now assume that you have an algebraic group defined over Q. Then you have two actions on the function on this group. So you have G and Q, and G of A acts on functions from G of A to L. So in the following way, so if you have gamma in G of Q, you let it act by translation on the left. So gamma phi of X is phi of gamma minus 1x. And if you have G in G of A, then you let G act on phi by translation on the right. So because you have left translation here and right translation here, these two actions commute. And which means that if you have a space X of function on G of A, which are, well, maybe I can take L or OL, for example. I mean, in fact, you can put anything you want here. Will not change. So if you have a space of functions like this, which is stable by both actions, then you can look at the cohomology of the discrete group G of Q on the space X. And because you have used only one action, you still left with the other action of g of a. Okay, so that's a way to construct a representation of g of a, which are interesting. And basically, a big part of the p-adic Lagrange program is to understand this kind of spaces. Okay, so now the question is, what kind of space do you want to put here? So examples, maybe I put them here. So the first one is a continuous function. So you take C, which is going to be the continuous function from g of a to L. So that's the continuous function. And so in particular, this implies that such a phi is constant modulo the connected component of the identity. So this L is a finite extension of QP. So its topology is totally discontinuous. So if you have a continuous function, then it has to be constant on each class modulo g of r plus, which is because this is connected. Okay. So that's the most obvious thing you can do. Another thing you can do is take inside here, you take the set of phi which are continuous, but you want the continuity to happen only at a place at P. So you want it to be locally constant outside of P. So phi locally constant as a function of x outside P. So it's already locally constant as a function of x infinity. X, I mean, a function at a real place because of this. And so you want it to be also locally constant at all places except P. And at P, you really want to have a continuous function. You don't put any any further condition. So inside here, you have the locally analytic functions. So the phi in CP. So they are already locally constant outside P. And you want to be them locally analytic in XP.
This notation is parenthesis R?
What? G of R plus.
No, the E.
Oh, it's P?
It's a P. It means P and P, the same P. It's the same as here, too. So locally analytic in XP. So they are already locally constant outside P, and at P you want them to be locally analytic. So locally analytic, so you have function of, well, I mean, G is an algebraic group, so if you look at the QP point, it can be viewed as the analytic variety over QP points, and then you want the function to be locally analytic, so locally expandable in power series with respect to a chart on your variety. And finally, inside here, you have what I call LP, which are the locally algebraic functions. So phi is locally algebraic. And so it means that locally, it's, so here you have an algebraic group, and so locally it's a polynomial in the coordinates of this algebraic group. Okay, and this you can decompose using irreducible algebraic representation as a direct sum over all W of LC tensor W star tensor W. So LC are locally constant. The W here are irreducible representation, irreducible algebraic. So these are finite dimensional representations. And so the W star here, so G of Q acts trivially on this one.
So these are irreducible representations of G of Q.
These are irreducible algebraic representation of G, but in fact, G is going to act only through G of QP. Reducible algebraic, let's say, of G of QP. And here on this one is the G of QP, which acts trivially. Okay, so that's the typical space X that you can put. But if you want, you can add some extra requirements. So for example, here you can fix the central character, or you can do many, many things. Okay, so let me give you some examples of spaces that you get in this way. So I'm not sure how low I can write. Probably not much. Can I write here, for example? No? Okay, well, I will see. Very funny. So now what do I do?
It's a surprise for you.
Well, maybe I can still do something here.
Maybe you can use a different
Yeah, maybe this one is not so good. Huh? It's a pity because it was a very good marker. And what about this one? This is better.
I think Ricardo did it. You did it this job.
Ah.
No, we have alcohol, so it's fine, I think.
Should come out, right?
No, we take one.
That's you?
So maybe we should have a tea now.
Maybe there is a better.
No, see, I mean the next one here is much better. The one I have now, you can erase.
No, I mean another.
I hope this is recorded.
Yeah, it is. Live broadcast.
This one is good.
One moment.
Yes, yes, yes.
Yeah.
La mesa llena de permanente, ¿no? Debe haber cometido un error durante la charla antes. ¿Y puedo echarla así nomás o quedará mal? ¿Y le echo así? ¿Ves si lo saco un poquito? Did you not have this last week? Or was it a new pen?
I think it was a new pen.
Luckily we're on delay in time, so.
Well, it's good I did not fill up the entire board.
No, a que sale sí. A que sacar con sí, sí, no fue. Quiere decir que el paño tiene que estar húmedo.
¿Qué significa raspa cuando quieran escribir de nuevo?
For security. Only this one?
only this.
This one works.
No.
No, it does. Look.
Pásale el paño, ¿eh? Pásale, por favor. Ahí sí, ahí sí.
Okay.
Ah, you see?
Yeah, but I'm sorry. I prefer.
But it works.
Yeah.
Sí, porque hay que sacar el cocina.
Okay.
¿Ves que todo tiene solución? Ahí sí.
It's good, it's good, it's good. Gracias.
Consigue otro papelito para limpiar. Ay, que yo sé que bien, muchas gracias. Quedó mejor que a...
Ahora quedó bien ahí, ya.
But it was expressed was a joke to show you some funny moment. Oh.
No, wait. I want to try. Okay, so now my talk has disappeared, but
So we will...
okay, so I hope that everybody remembers what was on the board because I'm not going to rewrite it. So let's do some warm up. So we can start with G equals GA, the additive group. And so there is a simple lemma that tells you that if X is one of the space I introduced, C, CP, locally analytic, locally polynomial, or LC, then you can write X of G of GA as So this is a representation of G of Q, and it is the induced representation from G of Z to G of Q of X of G of Z hat. So G of Z is just Z, I remind you. So why is this kind of thing true? Is because you have a surjective map from Z hat to, cross R cross Q to A. And the kernel here is just Z. So this Z is this one. And I put G equals GA. The lemma is not general for any G. It's going to be true for G of A, for the GA, almost true for GL2, not completely true for some other groups. But I mean, something like this is going to be true always. Some variant. But this precise statement, no. Yeah, and so once you have that, Shapiro tells you that the cohomology that you are interested in, G of Q with value in X of G of A, this is the same thing that the cohomology of G of Z with value in G of Z hat. Okay, so if you write it in this way, it looks much simpler because you went from Q to Z. So Z is just a group generated by one element, so you know how to compute the cohomology of this kind of group. And this is much smaller than, X of G of Z hat. So this is much smaller than this. But on the other hand, you lost the action of G of A. Here you can see the action of G of A. Here you cannot see it anymore, but it's still there. Huh? Okay, so once you get that, then you get the following results. Proposition. So you can compute HI of G of Q with value in C of G of A, with value in OL. And this you get OL if I is equal to 0, and you get 0 if I is bigger than 1. And what is more interesting is what you get if you do the same thing with locally polynomial functions. Locally constant function, otherwise it's not clear what locally polynomial would mean. Then you get, what do you get? You get OL if I equals to 0. You get L if I is equal to 1. And you get 0 if I is bigger than 2. So I want to point out that here you start from something which is an OL module, and here the cohomology that you get is an L vector space. Okay, and that's one of the reasons, why it dies here, because going from a locally constant function to a continuous function is basically taking a completion. But if you take a p-completion of something which is a p-divisible, it's going to disappear. Okay? So that's one of the reasons that sometimes you see classes in the cohomology of locally algebraic functions, so classes which are classical, which disappear in a completed cohomology. Okay, and so why is this and why is this 0? So that's because there is a R measure for locally constant functions, and there is no R measure in p-adic for continuous functions. No measure which is variant.
Can I ask why your
Well, I will answer this question in 15 minutes, okay? Yeah, that will be better there. So the next example is G equals GM. So to answer Madden's questions, here you have the same lemma as here. Lemma, so X as above. Then you have two answers depending on what you are interested in. So if you look at the functions on G outside infinity, then what you get is the induction from G of Z to G of A of the continuous of X of G of Z hat. So this G of Z is not a very complicated group. It's plus or minus 1. But if you look at the function on G of A, what you get, maybe I write it here, X of G of A. This is the induced representation from G of Z plus. So this means G of Z intersected with the connected component at infinity of 1 to G of Q of X of G of Z hat. And this is even simpler than this one because this is just 1. Okay, so you see there is a small difference between this case and this case, is that you have to take the connected component. Then I told you that there is an action of G of A. What is the result? Then the proposition, let's say, is that well, this HI of G of Q with X of G of Z hat, G of G A, well, when you obtain is X of G of Z hat if I equals 0, and it's 0 if I is bigger than 1. Okay, and then I told you that there should be an action of G of A on this space. And what is this action? Well, it's just given by the fact that A star mod R plus star Q star, this is isomorphic to Z hat star. Okay, so this A star acts through the quotient Z hat star on this G of Z hat. And so let me remind you that G of Z hat is just Z hat star, okay? Because we are in GM. Okay, so that's already some non-completely trivial results. So, but let's go to a more interesting case. So G equals GL2. Then we denote by gamma the group G of Z plus, which is nothing else than SL2Z. So I remind you that this gamma has a nice presentation. So it's generated by element I, which is -1, 0, 0. I mean, this one plays no role, but I just put it still there because it plays a role in the relation. And you have relations, and the only relations you have are that E cube is equal to S square is equal to I, and I square is equal to 1. Okay, and the lemma now, so it's a consequence of the strong approximation theorem for SL2, tells you that X of G of A is the induced representation from gamma, which is G of Z plus, to G of A of x of g of z hat for any x as before. Okay? And so you can use Shapiro, like here, and what you get from Shapiro, plus the fact that your group is basically a free group with two generators, you get that, well, hi, what do I call it, of g of q x is 0 for I bigger than 2. And for 0, you get something which is not very interesting. What you just get is x of z at star. And now how does the g of a act on this one? It acts through the determinant. So the action of g of a here, the determinant goes to a star, and I explained to you that a star surject on z at star. Okay? Yeah, but I inverted the p everywhere, so. Because I have L.
Okay,
Yes. You are right. But I cheated. It's true that you would prefer not to invert 2 and 3, but let's. Okay, and for H1, what you get, so if M is a gamma module, so you will apply M to C of G of Z hat. To X of G of Z hat. Then the H1 is computed by the following exact sequence. H0 of gamma M. And here you have M S equal 1. M1 plus U square equals 0 goes to H1. And the map here is just multiplication by U minus 1. So you get a complete description of the space you wanted. But of course, you wrote it in a way that the G of A action disappeared, so it's very difficult to recover it from this description. But still, this description is quite good if you are only interested in properties of this module that depends only on G of ZP. And so, for example, locally analytic vector, locally algebraic vectors, and so on, they only depend on the action of G of ZP here. And this formula is just sufficient to prove many results. Okay, so now let's answer the question about completed cohomology. So relation to completed cohomology. So you have the following proposition. So the first thing is that if you look at H1, so the only interesting one is H1. It's still G equals GL2, G of Q with value in C. Then this is isomorphic to, you invert P from the cohomology, integral cohomology, so H1 of gamma with value in C of G of Z hat with value in OL. So the proof of this goes in two steps. The first one is Shapiro that goes to gamma but with L, and then you use the fact that this is compact to say that any continuous function with value in L is actually bounded, and so you get this kind of statement. And then the second part is how you can describe this group. So H1 of gamma with value in C of G of Z hat OL. Well, then this is the projective limit over n of H1 gamma C of G of Z hat with value in OL mod P to the n. And this is the projective limit over n of the inductive limit over big N of H1 of gamma value, so continuous function of G of Z hat mod n, but Z hat mod n is just Z mod n with value in OL mod P to the n. So that's just because Z hat is compact. So if you have a continuous function on a compact with value in a discrete thing, then it is actually locally constant. And so that's what we write here. Okay, and this you can still write as the projective limit over n of the inductive limit over big N. And so now you use the comparison between the group cohomology and the group cohomology of some classifying space. And so you will get H1 of gamma, sorry, no gamma anymore, H1 of the modular curve y of n. You take the C point of this modular curve and with value in OL mod P to the n. So this modular curve is a modular curve defined over Q. So when you take C points, it's not connected anymore. It has a connected component, which are the group is Z mod n star mod plus minus 1. And so if you look at this definition, this is Emerson's definition of completed cohomology. So that's what Emerson defined as a completed cohomology. Okay, and now this is Betti cohomology, and now Betti cohomology is the same thing as étale cohomology. So this is also isomorphic to H1 of Yn. So now it's a modular curve defined over Q, which you base change to Q bar with value in the same thing, OL mod P to the n, and so you get action of Galois, which is very interesting, but I'm not going to say anything about in this talk. Okay, so that's usually the way people define completed cohomology. So you take this completed group, then you invert P, and you get the group I just defined in this way. So now I let you choose whether this definition is better than this one or not. My point is this one is better, but and also one of the advantages of this definition is that you actually see the action of the adelic group, and here you don't see it anymore. I mean, it's not so difficult to pull it out, but okay, and so you can do the same thing with CP, and remark, if you do the same thing with CP, then what you get is you get L tensor OL, And then you get inductive limit over n prime to p, because now you are forcing everything to be locally constant outside p, and then you get the projective limit, inductive limit, and so on. H1 et al. Yn p to the k q bar OL mod p to the n. And this is usually the space that people consider. It's only completed in the tower, in the P tower, and not completed outside P. Okay, so that's what I call Emerton semi-completed cohomology.
Can I ask a stupid question?
I'm not sure, but you can try.
So, make a difference between C and CP, right?
Yes, there is a big difference between C and CP, yes.
So you're saying that there's some useful functions from like P to QL or to R which are not constant?
There are functions which are continuous from QL to QP, yes, which are not constant.
But in all this theory, like we usually take locally constant as the second thing. So
Yes, because people are lazy, they usually take locally constant functions, yes.
yeah, that's what I want to confirm with you. Only because they're lazy.
Well, not only because they are lazy, but mainly because they are lazy. They take. And also because, I mean, it's already complicated enough with p-adic functional analysis, and if you put continuous functions everywhere and not locally constant functions, then you are going to end up with an infinite tensor product of Banach spaces. And there is a way to handle this, but nothing has been really written in the literature. So, but still, I think it's mainly because people are lazy, and also because people believe that interesting Galois representation should be ramified at only a finite number of places. But one can also challenge this claim. Okay. So now let's me tell you what is the relation between all these groups when you vary the space here. So the first theorem is the following. Is that actually this H1 of GQ with value in CP, you can recover from a completed cohomology in the following way. So first, this is the inductive limit over Kp. So these are open compact subgroup of G, outside P, of H1 of G of Q with value in C of G of A. So functions which are constant modulo Kp. And this is, so each of these space is actually the fixed point by Kp of the continuous cohomology. Okay. So this is not a tautology. It looks like a tautology, saying that, well, if you have something which is invariant by Kp, it should come from the Kp invariant here. But actually, what you have to do, you have to tensor this exact sequence that was here. So you have to take this exact sequence and then take fixed points by Kp of all the terms. And for M equals this space, X of G of Z hat, okay? And so now you need some vanishing statement. So there is a lemma, which is a stupid lemma, which tells you that if you have a sequence like this, an exact sequence like this, and if if with a group K acting, if H1 of KB is 0, and if H1 KA and H2 KA are 0, then this sequence of invariants is still exact. So you want to apply this to this exact sequence here, and this group here was the continuous function on the hat star. And so if you if you want to apply this lemma, you need the following facts. You need that hi of SL2 of FL with value in FP is 0 if for I equal 1 and 2, that's what appears here, and L not P. Okay, so you really need this kind of statement if you want to prove that this sequence remains exact by taking K invariants. And so that's one reason why this statement is not a tautology. And that's one reason why I can't prove this kind of statement for general groups, because I don't know enough vanishing theorem like this. So it's not clear what the correct statement would be for a general group, and I don't know if the general statement would be true. Okay. So what you get from this no, so what? This is classical. I don't know if it is easy. For H1, it's an exercise I did a long time ago, and and for H2, I just read the statement in the literature and was happy with the statement. I did not check the proof. So I cannot tell you whether it's easy or not. I have no idea. I asked someone which I thought should know, and he told me he doesn't know. So, and I'm not sure maybe you would know it for 1 and 2, but probably you would need more in general, more vanishing. Okay, so one thing that you get is that, so proposition, is that these groups that appear here, H1 of G of Q, with value in C of G of A mod Kp. Well, this is isomorphic by Shapiro to H1 gamma C G of Z hat mod Kp. So this is admissible as a G of Qp representation. And this is because if you look in this sequence, what you will get are these groups that appear, but these groups are just finite copies of G of Zp. So that would be a direct sum of G of Zp, of C of G of Zp, some R which depends on the group. So that's how you prove it is admissible. So this gives a strong finiteness condition, in fact, on these groups. And so from this, you get the following corollary, so theorem, which tells you that if you look at H of GQ, H1 of GQ with value in Cp, and you look at the locally analytic vectors, then this is nothing else than H1 of G of Q with value in LA. And so why is this true? Well, it's still you use this exact sequence here. And you use the fact that if you have admissible representation, the functor taking locally analytic vectors is exact. So this is one of the main results of Schneider-Teitelbaum. It's the exactness of the functor of locally analytic vectors, but for admissible representation. It's not true in general. So use Schneider-Teitelbaum.
So this is locally analytic with respect to representation of which?
So it's the locally analytic vectors, meaning so they are already smooth outside P. So you want them to be locally analytic with respect to the P component, G of QP. Okay. So use Teitelbaum. And so the final result in this direction is a result of Emerton that tells you that the locally algebraic vectors of computed cohomology are what you think they are. So the theorem, which is one of the main results of Emerton in this direction, is that if you take H1 of GQ with value in CP, so this semi-computed cohomology, and you look at the locally algebraic vectors, still for G, locally algebraic for the G of QP action, then this is the same thing as H1 of G of Q with value in LP. So this space here is the space of classical classes. So that's the space of class that come from modular forms of weight bigger than 2. And yeah, so I should have mentioned before that this is related to classical modular form. And this is related to p-adic modular forms. And this one here is related to over-convergent p-adic modular forms. So that was pointed out by Lou Epan and then used by Juan Esteban in a more general context. And so what this says is that you can spot classical modular form inside p-adic modular forms by just looking at locally algebraic vectors for the action. Okay, and so how do you prove that? Still the same thing. You look at this exact sequence, but now you have to tensor by a locally algebraic representation, and you have to take fixed point by by an open subgroup of G of ZP. And then you have to use a vanishing of H1. So use H1KW equals H2KW equals 0 if K is open in G of ZP and W is finite dimensional. These are classical results that you have to put in the machine. Okay. So there is a variant with compact support of everything. What do I want? Yeah. Okay, so cohomology with compact support. So it's defined by the following cone. You take the cohomology of the group. And then you map it to the cohomology of the Borel. And so B is the Borel. So by definition, you have an a long exact sequence like this, hi minus 1 B of Qm go to hi with compact support Gm goes to hi Gm goes to hi Bm, etc. And there is a nice proposition that tells you that the H1s with compact support of G of Q with value in any module. So G is still GL2. Otherwise, you have to put more parabolics. Then this is exactly the space of one cocycles. So tau goes to C tau on G of Q, but which identically vanish with C tau equals 0 for tau in B of Q. So normally you would have to quotient out by, you would have this kind of description, but you would have to mod out by something. But here, computation shows you that this is exactly this description. So for example, there is a nice consequence is that you can, so there are some elements which are called modular symbols. And so you can, so they live in the dual of the cohomology with compact support. And if you look at this description of the cohomology with compact support, then this is given by the following formula, which is very easy. So you take 0, infinity, you pair it with the cocycle, tau goes to C tau. And what you get, well, let's call it phi, so because they are functions. Then what you get is phi applied to this element S, which was 0, 1, minus 1, 0. And you evaluate at 1. But this one here is the one in G of A. Okay, so this is a cocycle. These are functions on G of A. And what I'm telling you is that I give you a formula, but I tell you that this is a classical modular symbol with which we can do many things. Okay, so let me tell you what is the relation between this cohomology with compact support and cohomology without compact support. So it's given by this long exact sequence. Okay, and then you have to compute the cohomology groups of the Borel. But the cohomology groups of the Borel, you can reduce them to the cohomology groups of the additive groups and of the multiplicative groups. And I explained to you how to compute them in the beginning. And so in the end, what you get is the following. So the theorem is that hi C G of Q C is 0 if I is not 1. And you have an exact sequence. Goes to the induction from B of A to G of A of the functions on Z hat star And then you have the cohomology with compact support. And then you have the usual cohomology. And then you have 0. And here, so this is supposed to be a representation of the Borel, the function on this. So you let the Borel act on this first through the torus. And so the torus is the idels A star, and then Z hat star is just a quotient of A star. So you get this, this nice relationship between the two. And so one thing to notice is that here you only get things that come from the Borel, so which are principal series. And so in practice, it means that for many arithmetical applications, there is no difference between this one and this one for arithmetical application. For other arithmetical application, it's very important to have this extra factor, but okay, and then you have the same statement, I mean, the same kind of statement if you replace the continuous function by the locally algebraic function. So HIC of G of Q with value in the locally algebraic functions. This is 0 if I is different from 1 and 2. And it's the locally polynomial function on the P star if I equal 2. And then for I equal 1, you have a long exact sequence like this, which looks a little bit like this one, but it is longer. LP of the hat star goes induced representation from B of A to G of A of locally polynomial function on Z hat star, goes to H1C, goes to H1. And then you have extra term, one that looks like this one, and B of A, G of A, LP, the hat star. But then this is a dual, and then LP of the hat star. Okay, so I want to make two comments. So this sequence is actually self-dual because you have a duality between cohomology and cohomology with compact support. And this dual here is not the topological dual, it's a smooth dual because everything is basically smooth. I mean, it's not really smooth, it's locally algebraic dual, but it's basically a smooth dual. What else? Yeah, and so you can do all the computation with OL instead of L. And so what happens is that this group, even if you put OL, is going to be an L vector space. And this comes from the fact that when you computed the cohomology of GA, in H1, for the locally constant function, we found an L vector space, okay? And so this is one of the reasons why it disappears here, because this is already divisible if you take integral cohomology. There, so that's all I wanted to say about the GL2. So maybe I have some extra minutes to speak about other groups, but I won't say much, but yeah, I should say that everything I'm saying you can find in a paper on my webpage called Exercice p-adic. And well, it's fun computations. I mean, most of the results are due to Emerton or even people before Emerton, but so other groups. So we start with G, a reductive group like GLN, GSPN, anything you want. So the point now is that G of Q mod G of A mod G of R plus G of Z hat. Well, this is not reduced to one element as before. I mean, in all previous cases, what we found is that this was one element. But this is finite. Huh?
It's an assumption of what you say.
I think it's true. What? Pi 0. No, I already... Yeah, this is finite, and so you take some G1 GR in G of A that covers all double classes, and then you define some arithmetic subgroup to be G of Q intersected with GI G of R plus G of Z hat GI minus 1. And then what you get is that X of GA, now it's not just, I mean, it's a little bit more complicated than before. It's the sum over all these i's of the induced representation from gamma I to G of A of X of G of Z hat. With a twisted action, which I don't want to spell out. Of G of gamma I. Okay, so you basically have the same description as before. That tells you that, in fact, the cohomology of G of Q is going to be controlled by the cohomology of this arithmetic subgroup via Shapiro. But it is a little bit more complicated. Before you only had one, and now you have a finite number of them. But that still allows you to prove many statements. So what it allows you to prove, and then you can use the comparison between the cohomology, group cohomology and cohomology of some classifying space. And so you get that, and then, so Shapiro's lemma tells you that you have to consider the cohomology of gamma I with value in some module. But this is the same thing as the cohomology of some differential manifold built from gamma I. Sorry. G of Q, sorry. Yeah, so if you have some gamma I module, you can compute its cohomology by taking this manifold here and putting some local system corresponding to M. And this can be computed via a triangulation. Of your manifold. And so you are going to get a complex that computes the cohomology that looks a little bit like this one, but more complicated. So this one had only two terms, and the complex that you are going to get uses a complete triangulation. But it's a fixed complex. It does not depend at all on the module you put. Okay, that's one important thing. And so what you get are many results doing this. So you get that Hn, so the cohomology group of G of Q, when you put C of GA, but you impose the function to be a constant modulo an open subgroup outside P. This is an admissible representation of G of QP as before. that's just a formal consequence of the property of the category of admissible representations. That's nothing deep. But what you get from this is that if you look at Hn of G of Q with value in Cp, so it's still the inductive limit of these things. So it's still Emerton semi-completed cohomology. So the reason why this is true is that if you try to compare the two, then you have some R limbs that you want to vanish. And if you have admissible representation, what you use is the fact that if you have a decreasing sequence of representation inside an admissible representation, then it stabilizes. And so what you prove is that everything is Mittag-Leffler, so there is no R limb, and you are done. But the question is, what about Hn G of Q C? So I told you that for G equal GL2, what you get is really Emerton completed cohomology. And here I don't know, because if you're trying to run the same argument, you have the same R limbs, but nothing is admissible anymore, and I don't know how to prove that the R limbs vanish, so it's a question. So what you get is that you have a map from this one to Emerton, but it could be a kernel which would be made from R limb of Hn minus 1. Anyway, that's another indication that this one is better because it's bigger. And then what the last result I want to mention is that from here, you also get, from this, using still a Schneider-Teitelbaum, you still get that Hn of G of Q with value in Cp. And if you look at the locally analytic vectors, then this is Hn of G of Q with value in locally analytic functions. That's the same proof as before, is because everything is admissible, and the functor of analytic vectors on admissible representation is exact. So it still works in general. Now the big question is, there are two big questions. So for local algebraic vectors, the result that I mentioned is completely false for general groups. You only have a spectral sequence. But the big question is, what is the relation between the completed cohomology and the semi-completed cohomology? So the question is Hn of G of Q with value in C, G of Z hat outside P smooth equal Hn of G of Q Cp. So I told you that in the case of GL2, this was not formal. It needed the vanishing of H1 and H2 of SL2 of FL with value in FP. Okay? So in general, I don't know. And so let me give you an example. So example, if G is the restriction of scalar from F to Q of GL1, of GM, sorry, GL1. So it's very simple case. Then this equality, so you take a number field F, is equivalent to Leopold's conjecture for F. So it can be that the only obstruction is actually the torus for this statement to be true. But as you can see, it's not a formal thing because it encodes Leopold's conjecture somewhere. So for all n, sorry. Equality for all n. I guess H1 is enough, but so why is because this one is 0 for n bigger than 1. For n equals 0, you don't need it. So for n bigger than 1, this one is 0, because that's due to a theorem of Chevalet that tells you that the congruent sum group problem has a positive answer for units in a number field. And this one is 0 only if Leopold's conjecture is true for P. That's a result of Richard Hill. Okay, so, but I should tell you that Leopold's conjecture is very easy to prove, but okay, so I feel I will end up here.
In the case of GL2, what are the algebraic vectors for H1 compact?
They are the H1 compact of the locally algebraic vectors.
They are the same.
Yes, they are the classical one. It's, yeah, I mean, it's not trivial.
No, I don't think so.
No. There is a proof in Emerton. I think there is a real proof in what I wrote, but that's quite complicated. Yes?
What do these results tell us about p-adic mentioned?
Well, it's not clear what they tell us. They tell us that these groups have nice properties, but now you have to actually try to understand what kind of irreducible representation are there. And that's another part of the program that I mean. So if you look at the case of GL2, there is a beautiful statement by Emerton telling you that this completed cohomology has a factorization, where on one side you have a Galois representation, on the other side you have a representation of the Adel groups, and they match one by one. So you can hope to have the same kind, I mean, a similar kind of statement in general. But the reason why Emerton can actually prove anything is that it's because we know something about p-adic local Lagrange for GL2 of QP, but we don't know much for p-adic local Lagrange for G of QP for any group other than GL2 of QP. So we are still in between. But still, so I mean, one important thing is that if you try to construct a p-adic local Lagrange for G of QP, then you need to check that what you are constructing appears in this group, in this global group. Otherwise, it tells you that you are doing something wrong. But, so there are test objects for anything you can do.
There are no more questions. Let's thank the speaker again. So there is a coffee break upstairs, and we will resume at 11:40. So 10 minutes late.
La première suite exacte, lorsque tu prends les fonctions continues, ok, je l'ai dans mon papier. En fait.
Ok, ben je te citerai. Envoie-moi la référence parce que je le mettrai.
Et est-ce que tu as des résultats sur la densité des vecteurs algébriques en général?
Non, je suis pas sûr que non. Ouais. Ah, j'enlève ça. Oui.
C'est sur les fichiers, ça.
ready. So welcome to the second talk of today. So our second speaker is Gonzalo Tornaria from Universidad de la República, and the title of his talk is Computing Paramodular Forms.
Okay, thank you. I want to start by thanking the organizers for putting together this wonderful conference, and we had an awesome week last week. So just so that all of you guys that just came are jealous of us. We had very, very nice courses last week. So, all right, and thanks for, I actually took this picture yesterday. It's a nice place to, anyway, so yeah, I want to report on some joint work with Neil Dumingan, Ariel Pachetti, and Gustavo Rama. Gustavo Rama is there, somewhere there. Where is Gustavo? There, okay. Okay, let me start with an introduction. I will try to introduce some things for those of you that are not familiar with stuff. This is a picture I like a lot. It's what we call the universe. This is coming from the lmfdb.org. If you don't know this website, the L functions and modular form database, it's a great place to wander around, to walk around and see objects. So imagine picture the Cremona's table of elliptic curves, but for many more types of objects, and they are all interrelated, and you can click and browse and see examples. So I'll show a very, very brief snippet, but you can go there. And this is the, I mean, we all know this, but I like this picture a lot. All the relations, L functions and modular forms here, and all connected in different ways, etc. So, and one of the key things that we care about is this modularity. I mean, modularity is all regulated by all the picture, but just to focus on this and to give some motivation for the paramodular forms. I mean, last week I was asked why paramodular forms, why not Siegel modular forms? I mean, paramodular forms are some kind of Siegel modular forms, but just to give an idea, so this is well, I guess it's already a classic result of the connection. So in the motivic world, you can think of geometry, and here you can think of analysis, modular forms. And so there's this connection between elliptic curves and modular forms, this sort of, well, bisection, at least over some fields we know how to prove this. And this is, of course, Shimura-Taniyama-Veil conjecture. There's work of Eichler-Shimura going one direction. And, of course, theorem of Wiles and Wiles et al. That actually proves that every elliptic curve comes from a modular form, every elliptic curve over Q, and et cetera, et cetera. So this is an instance of the Langlands program for GL2. And what we'll talk as an example, I won't talk about modularity today, but this is as a way of motivation. If you have an abelian surface, you can think of a curve of genus 2 and take the Jacobian, for instance. That's the easiest way to present an abelian surface sometimes. Then you expect some kind of automorphic object on the other side, and that's expected to be a paramodular form. Okay, so that's one reason. And the classical Siegel modular forms don't work completely well for this. I mean, there are not enough Siegel modular forms in that sense. So this is really an instance, thinking on the automorphic side, this is an instance of GSP4 being the group now, right? So and there's this was the first connection between abelian surfaces and Siegel modular forms was suggested by Yoshida, and then Brumer and Kramer about maybe 10 or 15 years ago, they made a very precise conjecture. I will state the conjecture later, but or a form of the conjecture, a precise conjecture relating these two, and there's a lot of evidence. And also, There's also work on looking at the Calabi-Yau threefolds, so three-dimensional varieties of a special kind, a different kind of generalization of an elliptic curve. And for some special types of Calabi-Yau threefolds, we also expect Galois representation, symplectic Galois representation of dimension 4, and this maybe should also correspond to paramodular forms. I mean, we have some instances of this connection, and so this is something. I should say about this, if you think of this on the Galois representation side, there's something you have to be a little bit careful. Here we think GL2 Galois representations with images in GL2 and GL2 automorphic forms, and GL2 is sort of self-dual group. And if you try to generalize these to abelian varieties, you of course get a Galois representation that is symplectic, and then when you do the Langlands correspondence, you expect to get automorphic representation for the dual group, which is not symplectic but orthogonal. It just happens that you look at the Dynkin diagram, you reverse all the arrows, but it just happened that for GSP4, the dual of GSP, it's just two dots with an arrow pointing one way for the symplectic and the other way for the other orthogonal. But so when you reverse the arrow, you get the same. So it's an instance of the accidental isomorphism there. So you still get GSP4. But in general, if you want to generalize this to higher dimensions, you won't get symplectic modular forms here. So you won't get Siegel modular forms. Anyway, so to focus on the automorphic world, which is on this side that I will talk about, and to give a summary of what I want to present today, let me start by recalling the classical situation when we are trying to understand modular forms for GL2 or automorphic forms for GL2. There is this correspondence. It's usually called the Jacquet-Langlands correspondence, but it has its origins in work of Brandt and Eichler that makes automorphic forms for GL2 correspond to automorphic forms for a quaternion algebra. Here B will be a quaternion algebra, okay? And so not every automorphic representation here shows up here, but it's very well understood which things can transfer from one group to the other. What you have to keep in mind is that GL2 is a special type of quaternion algebra. I mean, is the invertibles on matrices. So it's a split quaternion algebra, and so this is really. I mean, these two groups are isomorphic over the complex. I mean, so this is like a non-split version or an inner form of GL2. So that's why we expect a transfer there. Okay. And in fact, Jacquet-Langlands works with any quaternionic any quaternion algebra, but the classic version I referred to by Brandt and Eichler is mostly about definite quaternion algebras, where the automorphic forms or the quaternionic modular forms can be computed in a sort of combinatorial way. With less analysis or less numerical or things, so that's very convenient. And there's another relation between the quaternion algebra and ternary quadratic forms, so quadratic forms in three variables. Okay, there's actually a quotient. In fact, there's a map. If you make, for instance, you can have the quaternion algebra act on itself by conjugation. And you can restrict that to the trace zero part, for instance, and that's a three-dimensional thing. And this gives you a map from B cross to the orthogonal group, which has the center as the kernel. And so there's also a relation between modular forms here and modular forms there. So that's a classical picture. And if you want to do this something similar for GSP4. So it turns out GSP4 has an inner form, which is I call here GU2B. You have to think is some invertible matrices, 2 by 2 matrices in the quaternion algebra. So this is really actually matrix, 2 by 2 matrices on B that preserve some Hermitian form. That's the analog of GSP4. I mean, GSP4 is 4 by 4 matrices that preserve a symplectic form. And in the case where B is the split quaternion algebra, this is the same. But then, okay. And now this group, in a similar way to this projection, you have a connection to the orthogonal group in 5 variables. So, and these two I put in blue are the ones that I want to connect. So we want to understand modular forms for GSP4 using computing modular forms SO5, which we can compute much faster. That's the goal. And we want to give a theorem that relates the two so we know what we are computing. Okay? So this is main goal, explain how to use orthogonal modular forms to partially solve the basis problem for paramodular form. The basis problem is, I don't know, it's a name I like a lot from Eichler. It means to compute all the forms or whatever. So, yeah. And yes? So in principle, you can do, here you can do, it doesn't matter, you can do split or non-split. But for the purposes of computation, and the notation here sort of implies it, I'm picking quaternion algebra that are ramified at infinity.
Well, the reason I'm asking is that for GL2, if you're interested in weight 1 forms, you cannot transfer them to a quaternion algebra.
No. That's true.
Here you said abelian surfaces, so I wonder, like, these are not discrete series. Are you sure you can transfer them to
You are absolutely right. You are absolutely right. So that's a good remark. Thank you. So here I put of weight at least 3. So on this correspondence, if we do definite quadratic forms, we only get paramodular forms of weight at least 3, and the paramodular forms corresponding to abelian surfaces are of weight 2. So indeed, so the weight 2 is not homological. It's harder to access. So really, that's a difficulty that has this modularity business when you generalize. For elliptic curves, you get classical modular forms of weight 2, and they are fine. But weight 2 modular forms, that paramodular forms you expect here, are hard to compute, as hard to compute as classical weight 1 modular forms. You're absolutely right. That's one reason why we turn to look into Calabi-Yau threefolds. That makes that example interesting, because in that case, those are paramodular forms of weight 3. That's what we expect. So these are the ones we can compute. Okay. So yeah, absolutely. This method will only work for weight at least 3. But as any method using cohomology too. So if there were some method similar to modular symbols, it would only work for weight 3 or more as well. So, okay, and so one interesting application of all these is to prove congruences. So that corresponds to this part of the congruences have to do with the images of Galois representation. I'm not going to talk about this today, but in our paper we have examples of applications of this correspondence to actually proving some congruences, like some instances of the Harder conjecture and other types of, many types of congruences. Okay, so in this talk I want to do a brief review of orthogonal modular forms and how we can compute and about this theorem. So I want to introduce everything necessary to understand what this theorem says. What we prove is that every paramodular form of weight at least 3, even J, so this works for vector valued paramodular forms, and level P times M, where P does not divide to M. So we need 1 prime to exponent 1 in the level, and we think we're working on generalizing this to at least 1 prime of odd exponent, which would be everything except squares. But anyway, that's work in progress. And so every paramodular form with this condition can be recovered from some orthogonal modular forms. So that's a theorem. That's our main theorem that it was published this year in Mathematics of Computation. So, and well, it's not bisection, but we understand pretty much what shows up on the orthogonal modular form side. And orthogonal modular forms also include some forms of Yoshida type, and there are no paramodular forms of Yoshida type. But this is actually interesting. At first sight, it looks like, oh, we are getting stuff that we don't want, but it's interesting and useful, and sometimes to prove congruences, it's actually a benefit that we have these forms, because some congruences we prove going through Yoshida lifts. So anyway, so I promised last week that I will do a very, very, very brief introduction to paramodular forms. So this is going to be fast, but then you can ask me and see the slides or see a paper. So I tried to give an introduction to Siegel forms, which looks like classical. So if you understand classical modular forms, this is sort of made in this sort of enticing way. And this is how it's done. There's some, if you never saw anything about Siegel modular forms, there's some notes by Van der Kio on the archive. That's I like those a lot. There are many books, of course. So you start with the role of the upper half plane is taken by the upper half space. So basically, you repeat definitions using matrix G by G matrices. So it's just a space of matrices with complex values, G by G matrices. Imaginary part has to be positive as a matrix, and symmetric, and so on. The symplectic group is just a group of matrices, 2G by 2G matrices that preserve this symplectic form. And you can write gamma as a block like this. And these are the relations. I mean, this condition here is equivalent to these three relations. So you see, when G is 1, the prime is transpose, so this is nothing because it's commutative, and this is just saying that the determinant is 1. So this is just the definition of SL2. And this group acts on HG just by the usual way. You just have to be careful of which side you multiply, but you give this definition, everything works out. You can figure out the details. And so to define Siegel modular form of genus G, well, what you do in classical case, you have a subgroup of SL2Z. Here you want a group commensurable with SP2G of Z. We'll have some groups that don't have all integer coefficients, so that's why I put commensurable. And so a Siegel modular form is just a function from the upper half plane or the upper half space into the complexes that satisfy some relation like this. And here C tau plus T is a matrix, so you cannot just multiply by this to the k. You have to take determinant, and you also could take another representation. So determinant is a one-dimensional representation. You can take another representation, and you get this vector value. And anyway, so for G equals 1, you are used to giving this. Oh, it has to be holomorphic at infinity, or the cusps. And here, for G bigger than 1, this is not necessary by the Quecker principle. And here are some examples. The full Siegel modular group, would be level, we would call this level 1. There's the Siegel group, which is just matrices that look like gamma 0 of n. Just the stars are blocks, but it looks the same. This is the classical group, and it shows up in Siegel's work because it's the group that arises naturally for theta series. So for generalized theta series, for genus G theta series, you get modular forms for this group. And so that's why it appears. But in recent years, it's become more and more clear that the paramodular group is a much nicer thing, and you would not have a modularity result. I mean, Siegel modular forms are not enough to get, for instance, all the abelian surfaces. So really, the paramodular group is a nicer group. It's more natural. And it has a very nice theory of new forms. And so that's, anyway. So let me focus on G equals 2. So this works for every G. You have paramodular group, but the larger G is, the more paramodular groups you have, so to speak, because they are parameterized by a device or elementary device, a matrix up to elementary divisors or something like that. So for G equals 2, we just have one parameter for the paramodular group, which is what we call the level. So we have a level n, and the paramodular group is the matrices. We have to I say we need some denominator. So let's start with the symplectic group over the rationals and then intersect with matrices that look like that. So the stars mean integers, and then you need some multiples of n here. So this block would be all multiples of n for the Siegel. So this one would be multiple of n. It's not here, but instead of this, you have a multiple of n here, multiple of n here, and here you have a denominator n. Okay. And you can think of this as the symplectic matrices that fix this lattice. Okay, so SP4Z is the case of n equals 1. It fixes the canonical lattice, and this one fixes this. You don't see this, but you can actually rewrite the paramodular group as that, and then it's more or less clear that this is, well, I put this in gray, okay, so when you intersect with symplectic matrices, the two things are the same, and it's more convenient to write the paramodular group like this. Also, there's another. You could also replace the symplectic form by a different symplectic form. Instead of remember the J symplectic form was 0, 1, minus 1, 0, so you could put 0, 1n, 1n, minus 1n, minus n, 0. So you change the symplectic form, and over the rationals, all the symplectic forms are equivalent, so you get the same group, or isomorphic. But over the integers, they are not. And so if you change the symplectic form, then you can say, oh, the integral matrices, the integral symplectic matrices. But it's more convenient that all the paramodular groups live in the same symplectic group. So it's just a matter of convenience. Anyway, from the look of these paramodular matrices, you can conclude how the Fourier expansion of the paramodular form looks like. So as is usual with Siegel modular forms, you have an expansion like this. Now, be careful. So n here, the sum is n, it's down here, is a sum over binary quadratic forms. And this q to the n is just a formal way to write this term. So this is really like 3 variables, because binary quadratic forms have 3 parameters, okay, with sort of matches with the dimension of h, the upper half space. And because when you prove that, your modular forms are power zeros in Q, you use matrices of form 1, something, 0, 1. So you use translation by matrices here. And because here we are allowed to translate by a matrix that has an n in the denominator here, it ends up meaning that you get quadratic forms for which the first coefficient is multiple of n. So you get something a bit different. And yeah, you get some invariance like this with respect to gamma naught of n. So it's I don't know, it's different. Well, if n is 1, you get the classical definition of Siegel modular forms. And here you get this. Anyway, I will not talk much about Fourier coefficients anyway. So, and there's a canonical involution that splits the space, a plus part and a minus part. I mean, there are also local involutions, kind of like Atkin-Lehner involutions as well. But this is just the global, I mean, the canonical involution that gives you the sign of functional equation. The sign of functional equation for the L function. So there's several different L functions you can define for a Siegel modular form. Here I'll focus on this spin-order function, which is the one of degree 4, which is the one we care for the correspondence I was talking before. So it really, there's a theory of Hecke operators. So there's Hecke operators. There's actually 2 Hecke operators instead of 1. In general, for genus G, there's G operators. So, okay. And then the spin-Euler function is giving us an Euler product where the Euler factors are given like this. So it's just a formula, but is what comes out. And so you need to know, if you want to compute the L function, you need all the Euler factors. You need the 2 eigenvalues. So you take lambda 1, the eigenvalue for TP1, and lambda 2, the eigenvalue for TP2. I mean, you could put a p in the subindex here, but anyway. So for each p, you have 2 eigenvalues. That's what I mean. And then this, when you complete the L function like this, you add some gamma factors, some exponential, some. Then you get a functional equation that relates s to 1 minus s with the sign epsilon if f is an eigenvector for the canonical involution with sign epsilon. Okay. Notice I chose so this is like the Euler factor is with the arithmetic normalization, but here in the definition of L, I switched it here the k plus. Well, I move it here, so this functional equation goes from s to 1 minus s. So if you don't put this 3 halves minus k, this would go from s to, I don't know, k, 2k, I don't know. You can figure that out, whatever. All right, so that's sort of the crash course on paramodular forms. And here I promise I will state the conjecture, the Brumer and Kramer conjecture, which a version of it is more precise than this. But going in one direction, to every abelian surface of conductor n with trivial automorphism group, endomorphism group, ring, here I mean define over the rationals. So the abelian surface could have endomorphism, only not defined over Q. I should have put a Q here, but anyway. So for each one of these surfaces, there exists a cuspidal non-lift Siegel paramodular form of genus 2 with rational eigenvalues. And the converse is almost true, but not really. So you need to worry about abelian fourfolds. And it's like, okay, you have to, at a first version of the conjecture, say there was a bisection, but Frank Calegari observed this. You have to be careful about this. And before you say, why we don't get that for elliptic curves, we also get that for elliptic curves. But elliptic curves don't have endomorphisms defined over totally real fields. So it really only matters for, but if you want to do correspondence, modularity for elliptic curves over imaginary quadratic fields, for instance, to Bianchi modular form, you have to take care about that as well. So it's just, and there's also this, I mentioned Calabi-Yau threefolds, and there's this sort of, let's call it a quest for Calabi-Yau quest. When is a Calabi-Yau threefold paramodular in this sense? So whatever, and I just show a quick picture. So we want a Galois representation of dimension 4. So we better have the H3 to be dimension 4 for this to make sense. Also, if you know about this is the Hodge diamond. So for a Calabi-Yau, the zeros are because the Calabi-Yau property says that there are zeros here. So there are basically 2 parameters. Rho is like the Picard rank goes there. So everything in H2 is just algebraic, and you get Picard here, and you have something here, and A corresponds to the number of complex deformations of the Calabi-Yau. So the ones that would correspond to paramodular forms of weight 3 would be the ones with A equals 1. So this is like Calabi-Yaus that live in a 1-parameter family. So, and the examples there are is you have the 1-parameter family, and then you find specializations that have small conductor. It's hard, but that's what we find, how we find examples. Maybe you know about the case of the what's so-called rigid Calabi-Yaus threefolds, which is when A is 0. This is called rigid because they don't belong to any family, and the Hodge vector would be 1, 0, 0, 1. That's 2-dimensional. That corresponds to classical modular forms of weight 4, but the ones we would be interested are the one parameter ones. Anyway, so let's move to orthogonal modular forms. So again, now it's a crash course on orthogonal modular forms. So we start with the lattice in a positive definite quadratic space. Okay. So I always talking about definite spaces because, as I say, this makes computations easier because this gives us groups that are compact at infinity, so we can just not worry about infinity. That's the advantage. From a computational point of view, that's the advantage. So an orthogonal modular form, this is the simplest definition. You have to be more general than this, but this is a nice definition for a first definition. It's a function on the finite set of classes in the genus of L. So I'm writing gen of L to mean every lattice that is locally equivalent to L up to global equivalence. And this is a finite set. And so this is just a finite dimensional vector space. So the dimension of this space is just the class number of L. Okay? And well, the interesting thing, well, if you think about this from the point of view of automorphic forms, then it's more or less clear. But the nice thing is there's a very nice definition of Hecke operators that are given in a very self-contained way, like this. So if you have a function here and you want to compute TP, what you do is you take. So we want to know how much. What's the value of this in the class of lambda, so you take all the so-called neighbors, p-neighbors, so pi would be a lattice that is a p-neighbor, and being a p-neighbor just means there is another lattice in the same quadratic space, and when you take the intersection, this intersection has index p on both. And it turns out if you have a lattice, there's only a finitely many p-neighbors, so you just average or sum over all the neighbors. So it's like a diffusion problem. I mean, it's just what it is, but it's very easy to compute. This I put in sort of gray. I put some gray notes that are sort of asides, but you can actually replace this C here by a representation of the orthogonal group, and instead of requiring that this is invariant by classes, you require that when you apply an autometry here, this acts. So it wouldn't be functions constant in the classes anymore, but it's still finite dimensional. And so this representation is what plays the role of the weight. So for us, if we don't put weight, we only get weight 3 paramodular forms. But if you want to raise the weight, you have to add something like that. Anyway, so let me recall what I say was the classical case. This is very, very well known and has been studied for a long time, starting with Brandt and Eichler. If you start from the point of orthogonal modular forms, if you have a quadratic space of dimension 3, you can actually construct a quaternion algebra that corresponds to this space. It's called the Clifford algebra, or the even part of the Clifford algebra. So the Clifford algebra is 8-dimensional, but it has a mod 2 degree, so you just take the even part. But the interesting thing is that this the orthogonal group, the autometries of V are just the quaternion algebra, the invertibles mod center. So this is the inverse of the process. Earlier I say you take this group and you act on the trace 0 elements by conjugation. So that's how you go from one side to the other. And so from this isomorphism, it's possible to relate modular form for SOV with modular form for B cross with trivial central characters. So this is telling you the center has to act trivially. So that's what you get. And then you use the Eichler correspondence between quaternionic modular forms and classical modular forms to recover classical modular forms, and you can relate then ternary orthogonal modular forms with classical modular forms. There's a very nice paper, 1988 paper by Birch that used this for computations. It's a very fast method. Somehow related to Mestre method of graphs, but the Mestre method uses super singular elliptic curves, and then it only works for prime. And this is a bit more general, but I mean, it's the same in that case. And the limitation is that in principle, this computes only modular forms with sign +1. I mean, this is one of the limitations. Birch talks about this, if you've seen this paper. But you can actually fix this using certain characters on SOL. I won't talk about this. I worked this on my thesis a long time ago. So we know how to deal with that. So we get every sign, every possible sign. So this is not really a problem. And so what happened for SO5? So what happens if we repeat the construction, you start with a quadratic space of dimension 5, and if you take the even Clifford algebra, you actually get 2 by 2 matrices on a quaternion algebra, and the orthogonal group is really what I said before, the GU2, which is matrices that preserve some Hermitian form, modulo center, and SOV. So that's what I said. And there's essentially only one Hermitian form on B2, so that this defines the thing. And again, GU2B is a compact inner form of GSP4. So they are related by this. So you expect an analog of Jacques-Langlands transfer. It turns out some years ago, well, the analog of this correspondence, I like to call it Eichler-Jacques-Langlands, was actually conjectured by Ibukiyama for prime levels many years ago, later by Ibukiyama, more recently by Ibukiyama-Kitayama for square field levels. It's more or less similar, but you have to work out some details. And it relates paramodular forms, so orthogonal modular forms of GSP4 with modular forms of GU2B. That's just what I said. And the conjecture says what you expect on one side and the other. And this, under this condition, prime level or square field level. And recently it was proved by Rosen-Weissauer using some trace formula that the correspondence works. And we had to, they only prove it for square field levels, and we needed a slight extension to get to all the levels we want. But I mean, the real work on this correspondence is the work by Rosen-Weissauer. And our main result is the other side, the correspondence, the precise relation between modular forms for GU2B and forms for SOV, which from this isomorphism looks like, okay, it's isomorphic, so it's the same, but you still have to write some details and make this correspondence. I mean, it's more work than it seems, but that's been done. So this is our how the theorem how all this works. So as I say, we're taking levels of the form p times m, where p does not divide m. So we need at least one prime to exponent 1. Again, so the things in gray, you can choose to read them or not to read them. So if you want, you can choose A and B, 2 parameters. This is related to the weights. So if you want higher weights, you need A and B. Otherwise, you can pretend A and B are both 0, and there's still a very interesting theorem. We consider quaternion algebra ramified at p and infinity, so that's why we need the prime to exponent 1, because the ramified prime, we have some freedom. We could choose a different quaternion algebra, ramified at more primes, but we can we only did it for the ramified primes have to be exponent 1 so far. We think we can do it for odd exponent as well. And as I will remark later, for the same problem over totally real number fields, well, if you have an even degree totally real number field, you might get away with the quaternion algebra. It's not ramified at any finite prime. So anyway, so the theorem of Rosen-Weissauer, with the slight extension I mentioned, is that there is a discrete subgroup of GU2B. I call it purposefully, or maybe confusedly, I don't know, K of n. So this is not the paramodular group. This is the analog of the paramodular group in this inner compact twist, such that the paramodular forms of level n correspond to modular forms of GU2 of level K of n. So forms for the symplectic group of level paramodular n, so k of n correspond to modular form for G2b of level k of n. So this k of n here is different than the k of n here, but this is, I don't know. And this is saying how the weights relate. And this is actually a bisection for p new forms of general type. This means on this side, just like the classical Jagiellonians, on this side you only get forms that are new at p, so you don't get the old forms at p. And this is not quite a bisection, but if you restrict to forms of general type, then it is a bisection. And forms of general type are the one we care more, because the others you can get with lifts or other means anyway. So it's still, I mean, there's a precise correspondence, so you really know, like if you have a form not a general type, you know what to expect here, what multiplicity. So it's all very detailed. It's very important. These details are actually important for computation, because when you find a form and you think you have to decide whether it's a general type or not, and then it's useful to know what forms of non-general type you expect to be sure you are not seeing something that looks general but it's not, or stuff like that. So anyway, and Saito Kurokawa type, that's some type of non-general, appear on both sides with some multiplicity, and form of Yoshida type appear only on this side, not here, but still we can, I mean, yeah, we know what's the multiplicity of the Yoshida type here, so that we can discard. You see, from the computational point of view, if you find something that looks like a Yoshida lift, how do you know how many eigenvalues you have to compute to be sure? That we don't know. But because we can compute classical modular forms, we can compute the Yoshida lifts and say, okay, we expect to find this Yoshida lift, so with this multiplicity, so we throw it away. Anyway, that's a computational remark. Okay. All right. So the subgroup K of n, well, maybe similarly to what I explained about the paramodular group, the group K of n on this side, on the quaternion algebra side, is given explicitly. We give it explicit formulas, and it's really the stabilizer of some lattice on B2 on which GU2B acts. Okay, so it's similar. And well, you can identify, as I say, you can go backwards if you start with M2B. M2B is really the even Clifford algebra, some quadratic space of dimension 5. So this can go back and forth. It's a bit more complicated. It's not just taking trace zero elements or something. It's a bit more complicated, but it's something that you can do. I mean, you can easily use the involutions. There's two involutions here, and you can use the involutions to take a space of dimension 6. So this is dimension 16 because it's 2 by 2 by 4 for the algebra. So it's dimension 16. And there's a way to separate a part of dimension 6 and a part of dimension 10. And the 5-dimensional space is just the trace 0 in this 6-dimensional space. So anyway. Okay. So as I say before, GU2B mod center is SOV. And there is a lattice, a special lattice. We call these special lattices in V because they are of a shape we can compute easily. There's a special lattice in V such that K of n corresponds to SOL. Actually, it's the normalizer which brings to this issue with the sign of the Aitken-Lerner. So it's the normalizer. So in principle, doing this, you only get modular forms that are for which all the Aitken-Lerner signs are +1, but as I say, there's a way to fix that, and we do it. So, and so our theorem is that there's an isomorphism between modular forms for GU2B of level K of n and modular forms for SOV of level SOL. So that's it. So that's the other part of the transfer, and this is an isomorphism. I mean, there's no. I mean, we already jump from indefinite to definite, from split to non-split, which is where we lost some stuff in the correspondence. But here is really an isomorphism. Okay. So and this is the corollary, the way, if you connect both things, the way I stated before, every paramodular form of weight k, even j, and this special type of level correspond to orthogonal modular forms. Meaning, if we compute tables of orthogonal modular forms, we are sure we are going to get all the paramodular forms out of that. Okay? And some remarks. All our methods are local, so this works. This should work fine to arbitrary totally real number fields. Okay? And as I was implying before, if you have a totally real number field of even degree, you can use a quaternion algebra. It's just ramified at infinity, and then you can do arbitrary levels. So there's no restriction on the level. Okay. And for fields of odd degree, you need at least one prime to ramify. So, and we sort of have the idea of how to extend this to an odd exponent. Okay. And then we expect that you can get every paramodular form when the level is of this shape, which means not a perfect square, because anything that is not a perfect square has a prime of odd exponent. And for perfect squares, we could miss some paramodular forms. In fact, we expect, you expect to miss some, like in the classical case, you also miss some. Okay, so to sort of finish, we started 11:14, right? 40. So I got 10 minutes, something like that. Yeah. Okay, so let me give an example, because I like to be explicit about things. So it's going to be a very explicit example, but of course you don't compute by hand these things. You program. Or you ask Gustavo to program. So Gustavo has all of these programs. So and it's on the web page. So the programs are available. So here's the example. We start with this quadratic form. So it's an explicit quadratic form, 5 variables, x, y, z, w, and t. It has discriminant 61, actually half discriminant 61. The discriminant is really, the determinant of the matrix is 2 times 61 or something like that. But we computed 2 neighbors. I say the neighbors are finally many. So for dimension 5, the neighbors should be p to the 3 plus p to the 2 plus p plus 1, at least when p does not divide the discriminant. So there are 15 here. And if you compute them, it turns out 7 of the 15 neighbors are equivalent to Q1, 4 are equivalent to Q2, and 4 are equivalent to Q3. So we have a lattice. We find the neighbors. There are 15 neighbors. There are 15 different lattices. But maybe some lattice is equivalent to the original one. So in fact, 7 of these 15 lattices are equivalent to the original one, but other classes show up. And now you have to compute the 2 neighbors of Q2, and then maybe some new forms, some classes appear, and the neighbor for Q3, and so on and so on. And here are Q2 and Q3. And you keep computing 2 neighbors, so it's like you imagine it's a graph, or it's a tree, but the class makes it close, makes it finite, so it's a graph, and you keep moving until the graph closes, and there's nothing else to compute. Okay, and so there's a technical thing where how do you know you get all the classes this way? In this case, there's only one spinor genus, so in general. This process will span at spinor genus, and sometimes you have to take more than one prime, but that's some sort of technical. But in this case, we can be sure. And this actually gives 8 different classes in the genus of Q1. And the matrix. Okay, so I didn't write the matrix, but following this procedure. So the first column of the matrix is 7, 4, 4, 0, 0, 0. And so you write all of this. So you have your matrix, you compute the characteristic polynomial, and voila, that's the characteristic polynomial. You factor it over Q, and it has 2 rational eigenvalues, 15 and minus 7, and irreducible over Q. Of course, the 15 is of course clear, because if you just put the vector 1, 1, 1, 1, 1, because you are moving, every lattice has 15 neighbors, so 15 is an eigenvalue, of course. That's something like some kind of isostate eigenvector. And the third one, if you look at the polynomial and what we expect, what we know about lifts, this is really corresponds to a classical modular form of weight 4. This one, well, it's the only one I think. So there's a classical modular form of weight 4 that lifts to this one. So this is a lift. But there are no modular forms of weight 4 level 61 with rational eigenvalues. So there's no lift that could match this. So this is a non-lift. So that's the first non-lift. Actually, it's the first level for which there is a non-lift, or the first prime level. And just to note, there's actually a Calabi-Yau. We know a Calabi-Yau of conductor 61. And here it is. So it's this explicit formula. I say these Calabi-Yaus that correspond to paramodular form coming in a one-parameter family. I believe the parameter is like this term. If you multiply by a parameter lambda, then you get a one-parameter family of these Calabi-Yaus. And we actually know this is paramodular. So this is proven. It's not published or written, but it's proven. The way we prove this is we compute the Galois representation, or on the side, on the automorphic side. We know things about the automorphic side. We know things about the motivic side, and we do some sort of fault-insert method to actually prove this is. The two Galois representations are the same. So this is sort of proven. And a few more examples, not many, but okay, this is just a computation, how you compute this L function. Suppose you want to compute an L function, the L function. So this is an interesting, useful thing sometimes. So suppose you want the Dirichlet coefficients up to a bound x. So you need to compute the eigenvalues of Tp up to x and Tp2 up to square root of x. This is sort of the complexity. You need to compute p to the cube neighbors, all p to the cube neighbors for Tp1. And for Tp2, the number of neighbors grows like p to the fourth, but because you need only up to the square root of the bound, this is really I mean, the computing TP1 dominates the computation. So just as in this example of level 61, it takes 6 CPU months to compute the eigenvalues up to 3000. So that feels like a long time. It can be done in 5 days in our computer. That's an example. Computing this eigenvalue takes 2 CPU days. So CPU day is like if you use just one core in your computer, it will take 2 days. So that's that's how you measure. I mean, you could to compute this, you have to compute a lot of neighbors. So you could split your neighbor computation. If you have 1,000 CPUs, then you can split this computation in 1,000 pieces, and then it would take 1,000 of the time. But sorry. And I should say an open problem is how to obtain the Fourier coefficient. So I kind of cheated. We don't really compute the paramodular forms. We compute the automorphic form, meaning we know how to compute the eigenvalues, which is what we want for the L function. But the paramodular form actually has more information a priori, which is the Fourier coefficients. Of course, if by multiplicity 1, the Fourier coefficients, the information has to be there somehow, but we don't know how to recover it. So that's a disclaimer. We don't know how to do that. So let me just finish with whatever tables we have computed. So in 2020, we published a paper in ANTS with Gustavo with a table, companion table for all the way 3 prime level up to 997. The numbers in blue here are the number of eigenforms that appear in each computation. Later, we extended this to square free levels. This was before we knew the theorem, so this was conjectural. So there are 2,700 of them, of which, so this is all forms, and 684 have rational eigenvalues, which are the ones you would care for Calabi-Yauss or something. And some Dirichlet coefficients. There's a web page where these are available. Later, more recently with Eran Asaf and Watson Ladd and Gustavo and John Voigt, we did a larger computation, a larger scale computation using the same methods. And this is, by this time we already knew that theorem was true. The paper was already submitted by this time. So this was provable. So we computed some forms of weight 3, some of weight 4, and also some of, this is vector valued, so weight 3, 2, just to show. All of these should be or will be available in the LMFDB. Right now it's not available in the main LMFDB site, but there's like a beta version of the site here. It's called Pink LMFDB. Anyway, if you are interested in looking at this, you can ask us for the actual link. And so this goes up to level 1,000, and it becomes interesting for people that are computing Calabi-Yau to match the Calabi-Yaus with this. It becomes clear that it's nicer to have a larger table. So Gustavo is actually working right now on I think the computer is computing right now, right, to extending this table just for rational eigenvalues. Because at some point the spaces grow in dimension, and splitting the whole space becomes more complicated, but for some purposes we really want the rational eigenvalues, just like in Cremona's tables. So, and it would be interesting to compute the Dirichlet coefficients. I don't know, maybe we will, I don't know, that's a bit harder, or maybe not, I don't know. So this is our website, Gustavo and myself, and this is how the LMFDB looks like. It's just a snapshot. These two tables should be the same stuff, and so that's all. Thank you. So the credit for this picture is to Yang. A wonderful picture. Thank you.
Are there questions or comments?
In the perfect square situation, do you also have phenomena again like the multiplicity 1 doesn't hold anymore?
It's not about multiplicity 1, it's about some types of representations won't show up. I mean, we are not completely sure, but so all the representations that have odd this is it's just a local thing. So all the representations that have odd exponent in the conductor, they all have a particular way that we expect they will show up, and we think we can prove that. And for the even exponents, some will show up on the ramified side, and some will not. Like I can tell you easily, so there are many more types of representations for GSP4. But in the classical case, this is the statement. So a statement similar should hold. So Jacques-Langlands tells you that discrete series and supercuspidal representations show up on the ramified side, and so all you are missing are principal series, but principal series with trivial central character must have even exponents, and something similar seems to be happening for GSP4. Everything that has a reason not to be on this side has an even exponent. And so the classification is long, but if a lot of the types go away because they only have an even exponent, and other types of representation, all you're left is a few types of representation which have some instances with odd exponent and some instances with even exponent, but they both show up. Like the special series could be odd exponent 1 or exponent 2 in the classical case. They both show up in the quaternion algebra. It's just, anyway. So, yeah. It's not about multiplicity 1, but about something we'll know. I mean, it's not that we don't know how to prove it. We are more or less, I mean, I don't know if we can prove it, but I think it's more or less clear that some things will not be there at all. So.
From what we did so far, do you have a guess at which pot of gold lies at the end of the Calabi-Yau quest?
What? Do you? I don't know. One would tend to think that, you know, this is one parameter families should be all there. I don't know. Just because, you know, if you look at the Hodge vector, it's 1, 1, 1, 1, which matches this, and you know, it's a symplectic Galois representation. You expect them all to be automorphic somewhere. I mean, they have to be somewhere, and the paramodular forms. The nice property about paramodular forms is locally. See, if you have a representation that is a generic representation, they all have paramodular fixed vectors. That's what makes paramodular forms good enough. It's not true that every generic representation has a vector fixed by a Siegel group, but so I don't know. So that'd be a guess, but I don't know enough of the geometry to. So maybe there's another abstraction. I don't know. And these families are very hard to compute because basically you have, I mean, the equations are large, and there's basically a lot of families. Like there's 500 families, one parameter families of Calabi-Yaus known, and then you just have to plug in a rational value to the parameter and hope that the conductor is small. And so this is, it's kind of hard to come up with Calabi-Yau. That's one reason we want to extend this table, because, you know, the people doing this, we're not doing the computation on the geometric side, but people doing this computation, they come up with, they try to find out Calabi-Yaus with small conductor, and, you know, sometimes they say, oh, conductor is 1500, so they email Gustavo and say, oh, can you compute the paramodular forms for level 500, 1500, and he does, but we just want to put out the table so that it can be matched at least a bit more. So, yeah.
You say that weight 2 are connected to for weight 2. Can you say something for weight 2?
So for weight 2 is the one that Brumer and Cramer conjecture predicts that weight 2 paramodular are connected to abelian surfaces. But as it was observed before, we cannot really compute that using this method. We cannot compute this. These will not be automorphic forms for a non-split, a compact inner form. There won't be homological, so there won't be any kind of modular. I don't know if there's a modular symbol method for this, but even if there were, you wouldn't be able to catch weight 2. So the way Poor and Ewan computed these paramodular forms of weight 2 with a lot of computational effort, basically computing, you start with some lifts from classical forms, so you get some forms of weight 2, and then you multiply 2 of these weight 2 forms, so you get something of weight 4. And thanks to the fact that the multiplication does not preserve Hecke or lifts or anything, now this weight 4 you just hit by a Hecke operator to try to span the space of weight 4 modular forms, which we know a dimension formula, because this is homological, there's a dimension formula. So for weight 2, there's no dimension formula even. I mean, it's very similar to the weight 1 case. And so you span the space of weight 4, and then you have to divide, and then you have to do some checkup. This, you know, working out the weight 4 space is enough to know when to prove non-existence of weight 2 forms. But if you actually say you find one that looks like it's going to be, you know, this quotient looks like it's going to be a weight 2, but you have to prove the quotient is holomorphic or something. So in order to do that, you do another trick. You multiply again, and you have to span the whole space of weight 8 forms. And if you do that, then you can actually prove. And I'm not sure if it's been done for more than, you know, the first prime level weight 2 is 277. And for this one, it's been done. Pura you have a web page where they show the detailed proofs, and this is like involves spaces of dimension 12,000 or something like that. I mean, it's like it's big. I mean, so yeah, it's very hard. Way 2 is very hard computationally to find the forms. So.
When do you have dimension formulas for the spaces of tridimensional forms? When do you have dimension formulas for the spaces?
Ibukiyama has some dimension formulas.
For instance, weight 3, when do you know?
Weight 3, weight 4, yeah, larger.
Okay, so
at least 3. Yeah, it's always at least 3. From 3 up, it's fine. Yeah.
Okay, thank you.
That's how Rosneft saw it. I mean, they actually have traces. They prove some trace formula, so they can. I mean, it's you need something to make sure that it's just like Jagiellongas. You need a trace formula to be able to match one side to the other. So, and in particular, dimension formula. Yeah, but these were, I think, conjecture and maybe even proved for some cases by Ibukiyama. First for weight 4 and up, and then weight 3 is still a little bit more difficult in some senses, like in classical case, weight 2 sometimes is a bit annoying because you are in the edge, but it's still workable. Yeah, but weight 2, in principle, there's no, I mean, you don't expect to have a formula, right? So.
If you have no more questions, let's thank the speaker again. And if you want to come on Friday for the dinner, there is a piece of paper here, just write your name. We need to make the reservation, so please.